So welcome everyone. Thanks for coming out on this very, very dark November evening. I'm really quite excited to be talking about the work I've been doing recently on this Hurricane aircraft and the kind of really cool stuff that we've been finding and getting off the aircraft. So what am I talking about tonight? And why am I here? So this talk actually started out as a LinkedIn article. Based around me trying to understand what I was seeing. I was looking at a bunch of data and trying to understand it and scratching my head. And I decided that I went through a learning experience, so maybe it would be useful for other people to learn my process as well. So what the talk is really about, it's not so much about a bunch of analysis of dynamics and things like that, but I think it's more about understanding when you don't understand something. An example of the process of learning something to do, but most importantly, cool pictures of hurricanes and marine engines. That's probably why most people are here. So this started about with us strain gauging a Hawker Hurricane. So back in 2020, I was approached by the Battle of Britain Memorial Flight project team. And they wanted me to help them with Marshall Aerospace develop come up with a top level design to strain gauge one of these priceless vehicles. Since then, the design's been completed and installed in the aircraft and certified, and it's flying and it's getting data. So we're now getting to the stage where we can start to look at the data and try and make sense of it all. And this is basically where the story starts. The aircraft involved is she was called Last of the Many. When she left the production line, they'd written on the side her Last of the Many. Her tail number was PZ865. And she basically came off in the summer of 1944. So she is now 80 years old. The things I'm going to be talking about today, Hawker Hurricanes and PZ865 in particular. I'm going to do a little bit about strain measurement so you can understand what it is. When I show you something, some results, you can kind of understand where it came from and how I measured it, or how we measured it. I will talk about the Hurricane Loads Assessment Program spec, the whole spec that was developed and then implemented by Cranfield. And I'll talk a bit about the measurement of vibration and how do we actually understand data that we're getting off the aircraft. How do we turn it into something that we can visualize and get a feel for? And interpreting those results. Before we go any further, though, I am dedicating tonight's talk to Squadron Leader Mark Long, who we lost earlier this year. He was one of the pilots for the Battle of Britain Memorial Flight, and I never knew him. I only ever knew him from reading his scribbled poor handwriting on aircraft logs that I went through every year. The BBMF, the Battle of Britain Memorial Flight, just if you haven't heard of them, they're a branch, they're a squadron in the Royal Air Force. The pilots are all active Royal Air Force pilots. And they have 5 Spitfires, 2 Hurricanes, a Dakota, a Lancaster, and a couple of Chipmunk trainers that they use to keep the pilots kind of current on tail draggers. And you'll see them flying all over the UK in the summer months. The Hawker Hurricane. So it's a British design, stressed frame, so it wasn't monocoque. The outer wings are monocoque, but everything else is basically isn't a stressed skin structure. It's actually struts. Single seat fighter, designed in the mid-30s and flown a lot in the 1940s. Designed predominantly built by Hawker. It was built on license by other people. And Hurricanes accounted for just over 50% of all the losses of enemy aircraft down by British and Commonwealth forces during that conflict. So they were the main workforce. The prototype first flew in late 1935, and they went into squadron service in late 1937. And as especially as the Spitfire design continued to be developed over the World War II, the Hurricane became more of a, it just couldn't match the performance that it had, the performance that it had perhaps in 1940. So it became more used for things like bomber interceptor and ground attack roles and things like that. So, but it was still being used extensively. A lot of the success people attribute to its Merlin power plant. We'll be looking a lot at the Merlin tonight. So PZ865 in particular, so as I said, it was last of many. So there's a very last one off the line of 14,500. And its stablemate LF363 is the other BBMF aircraft, and they still continue to fly every year. Some specs, just so to get your head around what it can do. So its max max takeoff weight is a little over 7,000 pounds. It's 40-foot wingspan. It's 32 feet long, and her top never exceed speed is currently 3,300 knots indicated. She's got a PZ865 is currently running with a Mark 500 Merlin, which is basically a post-war civil variant. So they adjusted the design a bit to give it a bit more longevity, and so because they were operating civil aircraft that kind of not max boost all the time, basically. So it had a few mods for that, but it's basically the same as the Mark 20 that the Mark IIc basically started flying at. And it's got a three-bladed variable pitch propeller, and that becomes important in some of the things we're looking at later. The main thing about the variable pitch means you tend to see quite constant RPMs when it's flying between different flight regimes. So it'll be flying at quite constant RPM, and then it'll shift RPM and then shift down again. And you'll see that in a bit. So this is a PZ865 herself. I don't think I've got there. You can just about see my pointer. So the design is the wing design is the center wing is this structure here inboard of those dummy guns, and that is basically very much like steel girders. It's very kind of agricultural. Outboard, there's an outer wing, just here, which is like a stressed steel structure. The original Mark I Hurricanes also had like a girder outer wing, and they switched it for this kind of more modern design later. The fuselage structure is basically steel struts. And then there's formers on the outside and then dope fabric. And that was quite beneficial in that if you shot at it, the bullets tend to just go through the structure. Whereas if it's been a stressed steel, you might use the tail. The other thing to note is on PZ865, those guns are now dummies, and the gun bays have been taken out, and we now have fuel tanks instead. Okay, so stresses and strains. Given where we are, I suspect there's probably a lot of people who are aerodynamicists and not structures engineers. Is that fair to say? Okay, so this won't necessarily be a refresher. This will be brand new. No, you'll have all done it. So some very, very basic stuff on stresses and strains. So we'll cover what is stress and what is strain, and how do we measure strain, and something called the Wheatstone bridge, which has a couple of really useful properties when we're trying to measure loads on an aircraft. So for this, we've got to rely on something called Hooke's law. And Hooke's law allows us to relate stress and strain. So what is stress? Stress is about the internal forces within a structure. So if I've got a rod and I'm pulling on it, the forces within that structure is stress. And it's usually a force over a unit area. So because we're doing old school here, we'll be talking about pounds per square inch, not newtons per square meter. And strain is about the deformation that structure sees. So we have stress, we have strain. They're quite different things, but they are related, and they're related by Hooke's law. So to give an example, we have a rod of length L and cross-sectional area A, and we apply a force P to it, it will deflect that deflection value there. So stress in the rod, the internal force in the rod, in this case, if it's 1D rod, it's very, very simple, then we've just got P over A. So we've got pounds per square inch. it will deflect the value delta, and the strain is just the amount of deformation, so it's delta over length. You can, stress engineers will get into, is this engineering strain versus true strain and things like that. We're just doing a basic engineering strain, so just based around the original quantities. So we have engineering stress is P over A, engineering strain is delta over L. And if we have a continuous elastic material, then Hooke's law applies. And if it's a 1D rod, then it goes very simple. It just becomes stress is equal to the Young's modulus times the strain. And Young's modulus is just a measured quantity. It's basically like a stiffness value. Think of it like a distributed stiffness. And we can measure that. But once we know Young's modulus, it means we can relate stress to strain. So the takeaway is that if I want to know stress, if I want to know the internal forces, I can get at that by measuring how much the structure deforms. And that's the key to this measurement process. I measure the strain and I convert it to stress. Okay, so that means I've got to measure strain. So, not the only method, but a very common method is to use an electrical resistance gauge, and we will call this a strain gauge. So people have seen it. These things are actually really tiny. Like the gauges we have put on PZ865 are like that big. They're like smaller than my pupil. And we have a foil of metal that's conductive on a bit of non-conductive matrix, which we then superglue, usually, onto a bit of steel or aluminium. And there's like 30 layers there, which means that little strip of metal will extend 30 times as much as the steel underneath it extends. So how do we use that? So if we have this strain sensitive pattern here, and we put tension using Poisson's effects, you can, and also just think about it, you can, the structure will like thin out. So if it gets thinner, then the area reduces and the resistance increases. It's harder for the electrons to get through that length of wire. And conversely, if we compress it, then under compression it thickens up a bit and the resistance decreases. So what that means is I can just check the resistance between those two pads, and if the resistance increases, then that means I must be seeing tension, and if it decreases, I must be seeing compression. Or it might be the temperature's gone up or temperature's gone down, because you can get strain-free, stress-free strains as well, but we'll deal with that later. So it turns out this is, I think this is the end of all any equations you might see, but essentially what we've got is we've got a gauge factor, which is a constant, and we have, what it says is the change in resistance over the original resistance is the gauge factor is that value divided by the change in length over the original length, i.e. we now have strain is proportional to resistance, which means if I can measure resistance, I can measure strain, which is fantastic. Except any good engineer will then go, well, okay, so it's changing, but is it changing, by how much is it changing? Can I actually measure it? How much is actually a measurable quantity, or is it overcome by noise? So to get you a feel for magnitude, let's say we want to get a resolution of 100 psi. What kind of resistance change might we have to be able to measure? For this, we can go back to Hooke's law. So we have Hooke's law for the rod, which is stress is equal to Young's modulus times the strain. We have the Young's modulus, which is 30 million. So we can turn the Hooke's law around, and we have the strain is equal to the stress divided by the Young's modulus, which is 100 psi divided by 30 million psi, which means we've got 0.000003 strain resistance. Yeah, strain. We've got to be able, that's the level of strain at 1 psi. So I need to be able to measure a 0.003% change in resistance if I want to have 100 psi resolution. So that's that. To me, like I'm not an electrical engineer. That sounds difficult to me.
Exactly. Why didn't everybody give up at that?
That's right, yeah. Completely idiots. So we have a secret weapon in our back pocket, and that is a Wheatstone bridge. And we actually use it. We can use it for two things here. it gives us the sensitivity we're looking for, and it also gives us another special power. The first special power is sensitivity. So Wheatstone Bridge involves 4 resistors, a voltage source, and you measure the voltage difference across the middle of the bridge. Let's see if I can go here. So these resistors are basically strain gauges. So that strain gauge there is, is that long thin bit of metal. We're looking at the resistance. So if we stick resistor 1 and resistor 3 on the top of the wing, and resistor 2 and resistor 4 on the bottom of the wing, and it's just sitting there, and all the resistances are equal, and we have a voltage source here, do we measure any voltage difference between these 2 points? Yes or no? What do you think? Yeah, so if it's absolutely 0, then we won't measure any difference. And we won't measure any difference. So electron coming up here doesn't see any, there's no preferential path. So this is what we call a balanced bridge. But any tiny difference between these two, we'll start to see voltage difference. So now say we load the wing up, and so we put a force down on it. Now the resistors on the top, they're being stretched, so the resistance is going up, and the ones on the bottom, they're being compressed, so the resistance is going down. So now if you've got electrons that are trying to go up here, they've got a preferential path. They want to go up. So now we see voltage difference. And the differences can be tiny, and we still get to see the electrons want to go that way. So to give you a feel for how sensitive measurement we can make is that we measure 1 microstrain on a well set up system. So a system with a good amp and a good set of noise protection on it, we can measure 1 microstrain, which is the same as if we took a 1 kilometer long steel and we extended it by 1 millimeter, we can measure it. So this is the first superpower is sensitivity. But we also have another superpower. So what happens if we put the gauges? So we've got the very specific set of gauges. What if we put it in a different pattern on the wing? So if we put it in a different pattern, and we have R1 and R2 on the top, and say R2 is canted, like put at 90 degrees, so it's only measuring Poisson's effects, and R3 and R4, where R3 is in line and R4 is canted to the side. Now, what happens when we put a load on the wing? Does it stay balanced? So R1's increasing, and R2's increasing, R3 and R4 are decreasing. We don't end up, well, the thing is, we don't end up seeing a voltage difference, so it stays balanced. Whereas if we pull on it, then we do see a balance, and we get an unbalanced bridge, and we measure a voltage difference. So the takeaway here is that, like, don't worry too much about where exactly they are. The takeaway here is by changing the way I wire it, I can set it up so it measures tension but doesn't measure bending, or that it measures shear and not bending or tension. So I can now put gauges on around the structure, and I measure what I'm looking for. So that was the starting point with setting up Hula. So just to give you a little feel for what we put on the aircraft. So Hula stands for Hurricane Loads Assessment Program. The reason for it is PZ865 and its stablemate is 80 years old, and we want to keep flying them, but a lot of the original data has just been lost to the mist of time. We have some summaries, we have some basic bits of data. Steve's team have been doing amazing work, like pulling out what they can. And we know a lot, but we also don't know a lot. And also the original designers didn't know that much either. It was it was kind of the cowboy days for aerospace design. So this is a chance for us to learn. So the Hula's goals this is the overall goal. This isn't what I'm going to be talking about tonight, but this is what the reason why it's there, is to allow the BMS hurricanes to continue flying for as long as possible by measuring the load spectra and using it in fatigue analysis and establishing peak loads during displays. So making sure that they're not spanking it too hard is what I would normally say. So what have we done with the aircraft? Just to give you a feel for the kind of, this doesn't show the whole installation, that would, we would get quite bogged down, but to show you roughly where we're putting things. So we have, on the center wing, we have paired axial bridges. So they aren't bending bridges, they're an axial bridge on the upper spar and an axial bridge on the lower spar, on the front and back spars. We do the same for the outer wing. We have engine support axial bridges, so they're only measuring axial load. So if there's any kind of bending or offset in the strut, it doesn't get measured, which means we just know the main load force coming through. We do the same thing for fuselage struts in the aft section, and you'll see what they look like in a minute. And we have the vertical stabilizer spar bending bridges. So these are actually set to measure bending. And same for the horizontal stabilizer. And then we also have control surface torque tubes. They have torsion bridges that measure only torsion. So in terms of the overall number of bridges, we have 144 strain gauges set up in 82 Wheatstone bridges. So not all the bridges use all the 4 resistor positions. Sometimes we just have a resistor in, depending on the kind of thing we're measuring. We also have secondary bridges in critical areas. So a lot of the bridges on the center wing structure and outer wing structure on the main spars have actually got secondaries. So if the main bridge goes unserviceable for any reason, then we can revert to the backup. We're sampling at 16-bit resolution, so that means we have 64,000 gradations between clipping in compression to clipping in tension. And its current, well, it was in the inception, it was sampling at 500 samples per second, which for anyone who's used to OLM is like an insane level. For various reasons, it ended up being like that. It was probably higher than what was wanted, but all the bridges were at 500. But this is where the kind of serendipity happens, because this is where it allowed us to do some things we wouldn't have done otherwise. All the bridges have independent temperature gauges. So you can have a strain on the structure because the structure is being loaded. You can also have a strain on the structure just because it's being heated or cooled. The bridges, because you get a self-canceling effect, those bridges where all the resistors are strain gauges, the effect of temperature will self-cancel. But those aren't the only resistances in the system. You also have things like the wires. So the wires can heat up and the wires can cool down. And there are ways to get around that, but in this case, we've done it by measuring the temperature, and then we can do temperature correction. Then the bridges have local amplifiers. So very local to the bridge. Back in the day when I was working on OLM, operational loads measurement on like big hurricanes, big C-130s and things like that, we would have the amplifiers would be way far away from the actual strain gauge, but here we can have them very local. So there's a local amplifier which provides the voltage, because you need that voltage, and it carries out analog to digital conversion, and then it spits on a bus to a central logger unit. And then that central logger unit sends it via this control area network bus to the amplifier sends it to the CAN bus, via the CAN bus, and it gets recorded. And because this aircraft also has a parametric data gathering system, also records all the other stuff that's of interest, airspeed, altitude, and things like that. Here's some pictures of the install itself. So the install happened in its major in 2020 at Biggin Hill. And here she is looking quite different from the first picture you saw. So she's stripped right down. The outer wings have been taken off, and you can see the girder structure of the center wing. And you can just about in this picture see some of the fuselage struts, and you can see the engine struts out the front. Here she is from the back. And so you've got these aren't stringers. These are like formers doped for the doped fabric, which then provides like an aerodynamic surface. And then you can see the struts holding the empennage on. So this is, you can see the rear spar, and if we zoom up here, we can see the upper and lower spars, the strain gauge installations. So it's, unfortunately, these pictures, it's all covered up with like PVA. But here's where the amplifiers are. So they're providing the voltage which goes in, and then you're getting a voltage out, and then that gets converted and then sent down by the bus to the central logger unit. And the same on the lower spar. This is a fin spar, so this has got a bending bridge on it. So here we've actually got wires that complete the bridge. So there's two strain gauges down here, two strain gauges up here, and then wires that complete. And then because this has got a secondary bridge, I think, does it? No, probably got a secondary bridge. Then there's actually two pairs of them. And then to give you a feel for how the poor person who's actually got to stick these things on, this is on a torque tube, and you can see they're have to get a perfectly aligned strain gauge on a torque tube where they can probably just get 2 fingers in if they're lucky. And here's the central logger unit, and you can start to see all the wiring that is they have to feed in, and this is Steve's team's job to try and get that all in and not create a complete tangle. And another view there. And then this is her current, she's in night fighter colors, and this is what she currently looks like. Okay, so that's the install. Now talking about vibration. So I've been talking about how we're measuring loads and we want to understand the loads in the aircraft and things like that. Why am I looking at vibration? So we remember that we've got this really high sample rate. If you're doing like a loads measurement program on an aircraft and you're looking at a wing, you might be interested in sample excitations that are like 10 hertz below, but probably more like 3 hertz or below. 500 hertz is very, very high. But before we can get ourselves happy that we can reduce the sample rate, we need to be sure that there isn't actually a problem somewhere on the aircraft. So that might be because there is a normal mode in the structure that's the structure wants to vibrate at a particular rate and it's being excited. If anyone's seen Tacoma Narrows bridge videos, those are the most famous ones. The bridge is getting excited at a particular frequency by vortex shedding off the bridge deck, and it was being excited at that frequency, and then it started till it fell apart. So you might have a normal modes effect. You might have a buffet. You might have something downstream of protuberance, and this might be causing a problem. So we have to get everyone happy that there isn't a dynamics issue before we can reduce the sample rate. So we need to confirm there's no significant vibrations, and that means I was tasked to come up and with an assessment and go, oh yeah, is everything okay? That meant I need to understand what I was seeing. And I was like, I've looked at lots of vibrations on aircraft for years. The thing is, I was used to looking at vibrations from things like this. Turboprops and turbines, which are like butter smooth compared to a Merlin V12. So I was not prepared for what I saw, and I didn't know what I was looking for. So how do I look at vibration? So the main ways I can look in vibration is I can look at it in the time domain. So this is where I look at a voltage and I see how it varies over time. So I've got an example here. I've got a signal that's composed of 2 sinusoids, and I see the voltage over time. And in this case, it's really simple. There's not much going on there. I can just eyeball it and go, well, there's 2 amplitudes and 2 frequencies. I know what's going on. In reality, it's usually much more complicated than that. So what I can do is I can look at it in the frequency domain. So I can do what's called a convolution on it, and I can chuck away the phase information, and I can just look at amplitudes. And if I do that to the signal, I get this. So I get a high amplitude, low frequency, and a low amplitude, high frequency signal. I don't know when they're happening. I don't know what their phase relationship is with each other, but I can tell there's something. I can tell what's driving it. Now, if I take that frequency domain data and I actually cut the data stream up into little chunks, and I look and see how it varies over time, then I get something called a spectrogram or a waterfall plot. And I'll give you an example here. This is a spectrogram of someone saying the words 19th century. They've got time along the bottom, and I've got frequency from DC all the way up to 10 kilohertz. And you can almost see it like 19th century. You can see like the sibilance happening at the higher frequencies as it goes through. So this gives me a lot of information about what's happening at what frequencies, but how they change over time. And we're going to need that when we start looking at what's going on in this aircraft. So I've taken one flight of data from PZ865, and in this case, it's an engine strut. And I'm going to look at this engine strut in the time domain, but using a spectrogram. So here I have increasing time from left to right and increasing frequency, and it's going from 9 hertz up to 250 hertz. So I can't look any higher than 250 hertz because at 500 samples per second, 250 is the highest I can go because of what's called Nyquist. I can't look any higher. And DC is basically just a bit below the bottom there. And I look at it and I go, okay, there's a lot of lines on that. I was kind of, this aircraft was, for that particular plot, well, a lot of the time it's running at about 2000 RPM, which is about 30 hertz. So I was expecting to see, oh, well, there's probably something at 30 hertz, and then there's probably something at blade passing frequency, which will be 3 times that, and then there's probably going to be a few harmonics above that. And it's like, well, no, I've got all sorts. There's stuff here like 11, 12 hertz. There's something about 13 hertz, but then there's ones just below it and just above it. And I'm like, oh, I don't know what's going on. What's driving it? So to get a feel for that, I looked at just some basic parameters off the aircraft. So in this case, I'm looking at RPM, I'm looking at the signal, the channel signal itself, and I'm looking at aircraft G, W, just to get a first feel. So I've got RPM on the bottom, this is channel level, and there's our acceleration. And that's our whole flight. So we're bumbling along with the engine is kind of idling, and then we go to takeoff power, and then here's we get these long periods of very flat RPM because it's a variable pitch propeller, so it just stays constant RPM. And then this looks like something that you'd expect to see if you'd gauged up a bit that was affected by G, and it seems to be. So that all makes sense. So I can home in on a couple areas. So I've got this area down here where we got a sudden drop and then a stabilization, a sudden drop and stabilization in RPM. And likewise here, where it's stable, then drop, and then up. So if I go back now to this plot and look at the same spots, I can look there and there. If I superimpose the actual RPM, I get the same behavior. So this is all these plots all seem to be related to RPM. They're all kind of fractions or multiples of each other. So the next thing to do is to take one of the slices at a constant RPM and have a look at it, see what's going on. So here I'm going to employ a power spectral density plot. So power spectral density. So I'm looking at power in the signal. So I'm looking at a quantity squared. And I'm looking at spectral. So I'm looking at what frequency are involved and what is their density. That just means power spectral density. So here I have the same engine strut, power spectral density plot. Now the engine's at a set RPM of 31 hertz, 1860 RPM. And I can look at it and go, okay, here we are. I'm going to use a terminology here for, if it's the crank, I'm going to call it E. And if it's multiples of the crank, it might be 2E or 3E or so on. So here I've got 1E. So here's my crank. Fantastic. But I've got one here that's bigger. There's more energy going in, and it's at 13 hertz. I've got here one at 15 hertz, and it's not quite as big, but it's still pretty big. And I've got this one here at 39 hertz. And I'm really scratching my head at this point. Like, what is causing these things? So we have to start to answer it. We have to start looking at what are our possible sources of vibration on this particular aircraft. And once I've tagged all of them, or at least the significant ones, then if I know what they are, then I can exclude the unknowns. And if all the major ones are accounted for, then we're probably pretty happy. So sources of vibration are going to be, main one's going to be the engine. So as I said, I'm going to call it things like XE, like 1E, 2E, 3E, so on. If it's down to the engine crank. I've also got the propeller, and I'll call that 1p if it's at the propeller hub rotation rate, and 3p if it's at the blade rotation, because there are 3 blades, and so on. I also have the aircraft response to the engine and propeller. So if the blade is passing at 3p and we're getting blade wash hitting the horizontal stabilizer, we might see the lift varying at 3p. And so we might see bending at 3p. But we could also have, as I mentioned, normal mode vibration. We could also have buffet. These could also be things we need to worry about. So let's just have a quick look at the engine itself. So this is a Merlin V12, and at the front, we've got, this is the prop hub, and we've got a big reduction gear, because to operate efficiently, it actually has to be reduced in its rotation rate compared to what the engine wants to run at. We have basically two inline sixes that are at a 60-degree bank here. There's going to be a lot of bouncing around there. And then at the back, we have air inlets, and then we have the supercharger. So the supercharger, basically, because the aircraft is operating at high altitude, they need the supercharger to compress the air so that it's going to operate efficiently at where the air density is low. And that's also might be causing vibrations. So for the Mark 500 specifically, we've got this schematic here. And so we get the prop hub at the front, and then the air inlet at the back. And the first thing we look at is we've got the supercharger. That runs at 2 different speeds, but it's like a little over 8 to 1 or 9.5 to 1 ratio, which if we're operating at 31 hertz, mean these are going to be up around 250 hertz excitation. So these aren't our candidates. They're way too high for, that's way down at that. We could barely measure them using this system. So they're not the things we're worrying about. We got these 2 banks of 6 cylinders, and 6-cylinder, each of them on their own is called perfectly balanced, and they don't tend to cause a lot of vibrations, but they do vibrate. There is a certain amount of vibration going on, mostly from torque, which we'll get into. And in the front, we have this reduction gear, as I said, and that on this particular Merlin is reduced at 0.42 to 1. And 0.42 times 31 hertz is 13 hertz. So we've got our 1p load. So if we're seeing something at 13 hertz, it's something to do with 1p. We don't know what yet, but it's something to do with 1p. Okay, so to get into the engine itself and the crank, we just have to very quickly hit how does a 4-stroke work. And basically, the 4-stroke works by, it's got 4 strokes for 2 turns of the crank. So we have fuel and air going in, then fuel and air compressing, then ignition, power stroke, and exhaust. And a standard kind of configuration for those, you can kind of track around it. But the takeaway here is that you get a power stroke once every 2 revolutions of the crank. So part of the piston torque that we're interested in here is down to inertia. So this is force equals mass times acceleration effect. So the piston mass doesn't change. So that means the force is proportional to acceleration. So I need to understand how is this piston accelerating. And here we need a little force diagram. So if the piston is going up and down, it's going up and down once every revolution of the crank, isn't it? So we're going to expect to see some kind of sinusoid associated with that piston going up and down. That's called our primary source of inertia. Just going up and down as a sinusoid. But there's a secondary source, and this one's a bit trickier to get your head around. But if you think about it, as the piston's going down, if we've got, well, say my arm's the connecting rod. As it goes down, it rotates out, and it shortens as far as the piston's concerned. And then as it rotates back, it lengthens as far as the piston's concerned, and then shortens, and then lengthens. So 2 times every time the crank goes around once, it does this twice. And you get a dynamic shortening and dynamic lengthening. So we expect to see a sinusoid that's happening at twice the rotation rate. So here we have 1e at the rotation rate, where it's this sinusoid that's dotted. And we have 2e. This is the one due to the dynamic shortening of the connecting rod. It's happening twice. And then the combined effect is this heavy line. But if I look in the frequency domain, I'm going to extract out the two frequencies. So I'll see the two different sinusoids. So part of it is inertia. And from that, we expect to see a 1E and a 2E signal. Part is gas pressure. So during that ignition stroke, power stroke, sorry, we see the piston coming down like this. And if we do a force diagram, we see all the forces here are in balance, the forces here in balance, the force here is not in balance. So we expect to see, so we've got the gas pressure coming down is reacted by the connecting rod and the side force on the cylinder. And down here, this force in this direction is balanced by a side force 7 and a vertical force 6. But that force, that torque, is not balanced. So gas pressure creates a torque. And that torque happens once every 2 revolutions. So we have the power stroke where the force goes like this. If you look here, this is the average torque. The average torque over the cycle is actually really low compared to this like super peaky value here. This is why on a piston engine we see lots and lots of torque vibration. So we get this peaky load, and then basically we then have the exhaust, and then we have the inlet, then we have the compression. So this is the compression side. That generates this half order mode. So we expect half order, half time is this once every 2 revolutions. So from a gas pressure point of view, we expect to see half E. Now it turns out, and it kind of bends my brain to try and explain it, let alone completely understand it. But it turns out that you get harmonics of these modes based on like all the differences between because each of the different cylinders is firing at a different point, the differences between them mean you get harmonics. And they happen at 1, 1.5, 2, 2.5, 3, 3.5, 4, and so on. But it turns out that the 1s, the 2s, the 3s, and so on all cancel. So we only see 1.5, 2, 1.5, 1.5, 2.5, and so on. So this is another source of our, we've learned another source of our vibration. We also have piston firing frequency. So we've got a V12, and to make sure that none of the pistons are starved of air, or none of the pistons have problem scavenging the exhaust, they need to go in a particular order. And V12s, or all piston engines, will have very particular order of their firing so that they kind of maximize efficiency. So the 4-stroke fires once per 2 revolutions. Firing order affects the vibration, noise, and power, and also like how even the power is. And on our V12, it's that nightmare of a bouncing around. So 1 to 6 to 4 to 3 to and so on. Main takeaway from that is, as a V12 fires 12 times every 2 rotations of the crank. So now I have 6 times E as a signal. Okay, we're getting through it. Propellers. The propeller is also going to cause vibration, and we have something called 1P loads and NP loads. I first saw this when we were doing the A400M flying test bed, when they put a TP400 power plant on a C-130, and so this one power plant created as much power as the other 3 engines combined. And so we had a lot of problems and a lot of concerns about our 1P and NP loads. This prop is much smaller. It's still 11 feet diameter, and quite big, as big as a person. A 1P load is basically, if you think about the air approaching the disc of a prop disc, if it's approaching at the top of the disc, the angle of attack that the air makes with the blade is completely different from the angle of attack it sits at the bottom. So as the prop rotates around, the angle of attack is continually varying, and it's continually varying at the prop rotation rate. So you won't see this if the airstream is completely symmetrical with the prop hub, but it's never going to be like that. There's always going to be some slight offset. So we are going to see varying levels of 1P loads, which is basically just the loading moment on the hub that varies at 1 times the prop rotation rate. So that's our 1P. And then the other effect we've got is that these blades, none of them are aerodynamically perfect. They're all got slight variations, and there are also mass variations. So although the hub as a whole is dynamically and statically balanced, so there shouldn't be much of any of inertia loads, we are going to see some inertia loads due to the individual blades, and we're going to see aerodynamic loads varying at 3 times P. So we've now got, I think we've got our ingredients together. So if we now look at, we've got a table now, which means everyone's going to stop listening to me and read, but I'm going to put the table up anyway. So we've got 1P, which is basically prop disk aerodynamic forces, a little bit of inertia. We've got half E, which is our piston gas pressure causing a torque. We have 1E, so we have the piston crank inertia. That's the primary inertia forces due to the piston going up and down at the crank rotation rate. We have 3P, which is the prop blade, basically prop wash effects, either directly affecting the strut itself, or like the engine struts, or actually causing wash effects, say on the horizontal stabilizer. We have 1.5E, which is one of our higher order modes of the piston gas pressure. We have 2E, which is the secondary inertia forces due to the dynamic shortening of that of the crank, the connecting rod, that's happening 2 times the revolution because of the way it's swaying back and forth. And we have 6E, which is the piston firing rate. So now we can go back to our power spectral density plot, and we're looking at the engine strut again. We have our 1E. We have our 1P, which is now down to airflow effect, air inflow effects. We have the gas pressure. We have prop wash or prop aero hub moment effects. We have 1.5E, and we have 2E due to piston inertia or connecting rod effects. And then we have one, like some of them are superimposed, so 6P and 2.5E are actually right on top of each other. So, and you can, if you really zoom up and do a very long time period when you can get better resolution, you can just see there's 2 tiny peaks. So that's a combination of some kind of harmonic of the blade passing with the gas pressure. And here's our 6E. Okay, so that's the engine strut. What if we look at somewhere else? So this one's in a completely different part of the structure. So now we no longer have a big peak at 1E, but we have a very big peak at 3P. So this is a horizontal stabilizer. So 1P is pretty low, which makes sense. A half E is also low, which makes sense. It's quite far away from the engine. 1E is also low. There's a 3P, makes sense. We're probably getting prop wash effects happening. Second biggest one is 1.5E. What's that? What caused that? Torque, yeah. So I'm at the back, horizontal stabilizer, back of the aircraft. I can count the piston strokes on the V12 from here by measuring bending strain of a horizontal stabilizer at the back. That was when I saw that, it kind of blew my mind. So that's the main thrust of the learning exercise. So in terms of what we learned from that particular assessment, there's a lot of vibration on the aircraft. It's almost always associated with the engine and the prop or downstream effects of them. We understand what's causing them, or the big ones anyway. We don't appear to have normal modes or buffet issues, not anywhere we were looking at. So it's quite safe to reduce sample rates. And in terms of next steps for the project, so Hula sample rates have been reduced down to a bit more reasonable levels. We still have the data from quite a long period of time, so if we need to go back, we can look at it. I produced a proof of concept for generating transfer functions from the air calibration flight data. So we've done an air calibration flight where the aircraft flew a prescribed set of maneuvers, and I've created a loads model for the aircraft, and we've been able to tie them up quite closely, actually, between the flight maneuvers and what we were measuring. So there seems to be a good chance that we'll be able to get like decent transfer functions out so that we can turn the results, which are just in terms of like bits output from these strain gauges, into actual loads. And then once that data is created, then it will be used to create a load spectrum for fatigue analysis on the kind of major structures. This is just to think very quickly. So mainly, well, the big one is to the Battle of Britain Memorial Flight Project team. So they're the ones that have funded all this work. And the BBMF themselves, so the actual flight, so for actually flying and maintaining these aircraft. Cranfield Aerospace Solutions, they did the detailed design. I just kind of said, well, do that, that, and that, and here's a table, follow that. Design, implementation, cert, and tech support. And Cosworth for doing technical support is their system that did a lot of the measuring. And Musketeer Solutions for the data handling. And any questions? Though I know that Steve might want to jump in.
Yeah, we'll see what questions we get, Steve.
Oh, now that would be cool. I know there are, the thought is this would be the first of several.
Yeah.
So there could be a potential.
Yeah, so there's a particular, all of this work is there to improve safety. Okay? So the aircraft are safe, they're safe to operate now. The issue that's the elephant in the room with any old aircraft is, well, how long can you keep them flying? When my wife asked me, well, how long do you think we'll keep a Battle of Britain Memorial flight going? My glib answer was, well, until the oil runs out or we have another world war, you know. So, you know, the intention is to keep these going well into the century. With the fighters, as opposed to the Lancaster, there's much more emphasis on understanding fatigue. You've got much more redundancy on a big four-engined bomber, effectively. So there's one engine frame holding one engine. So to know how long to life that is much more critical than the four-engine frames on a four-engine aircraft. Lancaster might have this sort of attention in the future, but it's the fighters that are getting all the attention now.
Yeah, so, yeah, great question. Oh, sorry, yes. So the question was about calibration. How do you calibrate the temperature effects that happen on the strain gauges? And it's a pernicious issue with strain gauges because you can't tell if you're measuring, you can be measuring a stress-related strain or you can be measuring a temperature-related strain. The way we're dealing with it here is, to some extent, most of the gauges will not be sensitive to temperature to any great degree because A, our temperature ranges aren't very great, and B, the bridges that we're using basically self-compensate for temperature. So as one, if you've got a gauge like this and a gauge like this, they both expand to the same degree under when the temperature, but the amount that this gauge expands counteracts the one this one expands because they cancel each other out. But that doesn't cancel out the temperature effects on the wires that connect them all. And whilst there are actually ways to do clever electronics to get around that. That wasn't used in this case. But we are calibrating the gauges by comparing results. So what one thing I didn't say is that we can theoretically take a strain net gauge output, and because we know the gauge factor that was used, we can turn that into a strain value or theoretical strain value. But we're not doing that. Instead, what we're doing is we're saying, well, what is the load on the structure for that particular point in the sky? So we're doing a wind term and it's only G, and what is the load on the structure for that particular situation? And then how many millivolts are coming out of the gauge? If we were doing a ground calibration, which is often done as well, then you basically put a known load on. And when you do that, you can then extract out temperature effects because we can see how much does the result change that's excluded from that, the load effect. Because we can say, well, how much, if the temperature's gone up by 10 degrees, how much does the strain change? And then I can basically correct out the temperature effect. Kind of waffled with that, but the basic idea is that we're looking at the effect. We see how the gauge response changes versus temperature, but we're calibrating against a a predicted load in the structure. Does that make sense?
Based on flight data?
Yeah, so we do a flight, and so we have a flight where we have a point in this, basically a point in the sky, which with a known configuration of the aircraft, essentially a known load on the aircraft, and then we look at the strain gauges and we say what output is it in terms of, say, millivolts, and that allows us to basically calibrate the gauge. And then but for those gauges, we're also doing we're not only varying load, but we're also varying temperature. So we basically can see the temperature effect as a separate effect, if that makes sense.
I think I understand.
Yeah. Most gauges, though, are actually really resistant. They don't tend to see much. Also, the gauge materials themselves are actually formulated so that they are very insensitive to strain. You still get the temperature effects of some of the temperature effects due to the actual structure expanding and contracting, but for the temperatures that we're dealing with, they tend to be quite small. So the temperature-related strain is quite small.
Your criteria for cutting back your kind of frequency band. So what was presumably you've identified there was still a lot of high frequency spikes. Are you saying that, well, we understand those now and they're not big enough to cause a fatigue problem? And then we can not worry about measuring them?
Yeah. Okay, so the question was, what was the criteria for reducing the band, and at what point am I not worried, basically? Yeah, so that one's quite subjective. I think it's more about, there are going to be certain structures like the engine struts where we probably need to look at them and go, how big was that spike? Am I actually worried about it? Most of the rest of the structures, if I'm seeing a signal and it's in the wing structure and it's down to, and I know it's down to like piston excitation, I can almost say it's not going to be a problem because the magnitudes are going to be so low that, and especially because it's steel, the steel endurance limit won't come in to that, so I can just ignore it. There will probably be some structures on the engine struts where we might have to suck our teeth a bit and go, okay, so I might actually have to work out the actual magnitude. But still, if the biggest one there is like a 1E load, so it's down to piston excitation, it's probably low. The one, there's, yeah, and even like the half E stuff, yeah, so most of them are you're probably going to say they're probably okay, but it's a bit more eyeballing it. But
yeah, I guess you're making some kind of estimate of the fatigue damage.
Yeah.
And some of that's small enough, it's just not doing
Not yet, but downstream we will.
But at some point you can say, well, that's so small, it's not going to have an impact.
Yeah, exactly. And there is, so some of it is also based on experience in that I developed in the past some methods to do rough and ready eyeballing of is this vibration going to kill me or not and cause a real problem. And from that, you kind of know that you look at it and go, you can just look at the plot and go, yeah, that's not going to be an issue. But in the fullness of time, you need to, cover that off with some actual evidence. But I didn't see anything that really worried me. If you're seeing vibration where it's worrying you, it tends to be like totally dominating. Like you would be orders of magnitude above those. So great question, though. Yes.
Was there a reason you went for a Hurricane rather than a Spitfire?
Opportunity.
So the question was, was there a reason for Hurricane versus Spitfire?
Yeah.
I guessed it might be that.
Yeah, the opportunity. So, so the reason we picked the Hurricanes, well, the reason that the customer picked the Hurricanes was opportunity. That happened to be scheduled for what is a once in 8 year deep strip. The whole fleet have a once in 8 year deep strip, but the timing for PZ suited the project. There are reasons why, they have a fleet of 2 Hurricanes that are the same, so instrumenting one very closely covers the other one. The Spitfire fleet is more diverse, so reading across would have been more difficult. And this tubular structure is in a sense, it lends itself to strain gauges and understanding the output more easily than the monocle and semi-monocle.
So sort of cutting your teeth on the easy one first.
Yeah.
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 Which turned out to not be quite so easy.
Yeah. Proof of concept. Yeah.
Did you measure any effects when you dropped the carriage, or was it just very second order, literally lost in the It was only a fairly short period.
Yeah. I don't think we noticed many. You definitely saw the flaps. When the flaps went down, you saw it. Don't remember seeing much in the way of undercarriage, though I've not looked in detail in that at that data yet. But yeah, the undercarriage are connected into the center wing on the spars, so you definitely could see. You might see some kind of aerodynamic effects causing a torque on it. So you might see a fore aft load showing up. Yeah, good question.
Another question there. Having, as well as being an aerodynamicist, got involved in fatigue and trying to get, just really struggling to get my head around it, how difficult it is to calculate the fatigue damage. But I'm wondering with the aircraft, it's easy when you've got a structure, you know, a new structure, because you've started from, in theory, no fatigue damage. With something like this, how do you know where you're starting from?
Okay, so the question is, how do you know your starting point when you're doing a fatigue
It's
assessment?
an 80-year-old aircraft.
Yeah, I think I'll leave that to the man who's doing it.
Okay, so yeah, so on any particular components, you might start measuring 22, say, and that still leaves you with a question mark over the previous 60 years. Yes, that's a tricky problem. Now, we sometimes have an easier situation because, like triggers broom, it's not all the same components, and some of them we know when they were replaced. Okay, and they've been replaced during the period where it's been flying the displays it's been flying now, so you can extrapolate backwards to a certain point. When we get components that have been there from first build, it is going to be a much more challenging, and we'll probably do some rough and ready factoring for periods of time. If it's done over 500 hours, as an air racer, we might say, well, that's been twice as severe as it's being flown now, right? And it gets more approximate the more guesswork one has to do, but they're educated guesses, and we'll come to that as we start producing predictions.
Was it ever fitted with G counters? There is a flying RAF Bulldogs, and we had little mechanical G counters on those. They took a reading from in every flight. Although you had a nice flight sergeant, they reset it when no one was looking.
So the question is,
The question was about, did the aircraft have G counters? Not these individual ones. There was some experimental work, and in fact, I think you've dug out some of the papers where examples of Hurricanes, but also Spitfires and also Mustangs had G meters fitted. Am I remembering the right thing?
I think so. Yeah, and string, and G meters and string gauges as well.
Yeah.
Even in World War II, and other aircraft like Chipmunks have, or the Navy Chipmunks have G meters. Lancaster's got a G meter.
And you let student pilot here probably.
Yeah, so but not these aircraft, unfortunately. At least not generally.
So yeah, just to extrapolate that. If we thought that, I mean, this one hasn't really had a combat career, but if say this is a year of combats, then these wartime records would give us a reasonable indication of what that year had been like.
I guess a lot of the joints and bolts have been stripped down and remade over and over again.
Yeah. I mean, it's had an awful lot of reconditioning. Even the parts that are unchanged have been cleaned, checked for corrosion, reassembled. The joints use a lot of anti-fretting compounds, so that's all been refreshed. There's a lot of preventative care gone in. That trying to turn that into an effect on the numbers is going to be interesting, but it all helps with the safety argument that you can say lots of mitigation has happened.
So a question online from Richard Brown. I'm going to read its entirety because it's in two parts, so
Okay.
I need to sort of decode it. So really,
Okay, so the question is it the question is, does a perfect propeller have no 1p loads inclined? Yeah. So what happens is that even if it's the propeller disc, and it doesn't matter how many blades you have, is inclined to the flow, it will create a varying moment on the shaft, which varies at the 1p rate. So the individual blades, because of the go back. So the angle of attack is continually varying as it rotates around, and because of that inflow. So you kind of have to look at start to squint at these diagrams to see that the inflow angle will change for the blade disc at different points as it clocks around. So as it clocks around that blade disc, the lift generated by individual parts of the disc changes. So that creates a moment that varies at that 1p rate.
So yeah, your questioner is right about the balance and the inertia effect, right, for a perfect propeller, but the aerodynamics are unavoidable.
Yeah. Always happen. So you always get 1p loads. And so when we had the A400M flying test bed and we had this TP400, the first things we were getting from Airbus was basically, these are the 1p moments that are generated just by the fact at various points.
I think you have to distinguish between 1p loads on the blade and 1p loads on the hub.
Oh, yes, yeah.
Yeah, so you've got blade 1p loads, but I think Richard's point is that in principle your hub loads should cancel out because a 1p load at incidence in your, well, I guess in your aircraft frame of reference is a steady load. If you've got a proper incidence, then it's a steady load in your non-rotating frame.
We could go to my aerodynamic friend over there and go and give us a dummies go. Because 1p loads aren't just unique to this level, the universal issue. But maybe you're explaining it well enough. Go.
Yeah, I think it's all about frame of reference.
It will be, yeah.
Perhaps that's for another night.
Yeah.
Any more questions online?
that's the last one.
Okay, Peter, will you do the honours? Thank you.
Should I have a, or should I shout? Right, so it falls on me to do the vote of thanks. So Steve, thank you very much for a very interesting talk. I have to put my hand up and say that based on your initial article in LinkedIn, I was the one who said to the committee, we need to get him in, because I'm really interested in that and I want to hear more. So it's my fault that you got called out tonight. Yeah, really interesting talk. Lots of bits in there that got me thinking back to when I was at university, the revision of the stress and strain and so on, which is, I guess most of us here still understand. But yeah, the explanation of the Wheatstone Bridge, fantastic. It must be about the 10th time I've heard it, and I understand it perfectly now. I will forget it by the weekend, but it's great to hear it again. There's a very interesting detective story that you told as well, and that whole business of what on earth's going on here. Why am I seeing all this stuff? Really interesting and very well told, and just that transmission of vibration. You can see stuff that's happening at one end of the aircraft right down at the other end, and you can trace everything through. And I guess all of those modes are everywhere if you look on the whole aircraft.
Yeah, they're all over the place.
Really interesting. So yeah, fascinating talk. I'd be very keen for you to come back and tell us a bit more once you've done all the loads, the actual loads data that you thought you were going to be doing before, and what that means for the lifing of the aircraft. Yeah, if the rest of you in the room could join me in thanking Stephen for his talk.